Okay, welcome back to The Explainer. Today, we're diving into a concept that literally reimagines how computation works. We're talking about OMI. Instead of relying on the industry standard, which is just storing approximated numbers, OMI takes this radically different approach. It derives exact mathematical constants directly from geometric truths. It's just a completely different way of thinking about how our computers interact with reality.
I mean, it sounds completely crazy, right? But the truth is, traditional computers just store a cutoff, approximated guess of pi. They literally do not know the whole number. So today, we're going to look at why the OMI protocol completely rejects that inherently flawed system and what it actually uses instead.
Just take a look at the stark contrast here between how things have always been done and where OMI is taking us. Over on the left, you've got the traditional sign-value model. This is where a system is basically just guessing at reality by storing a fixed approximation. But on the right, that's OMI's place value model. It doesn't store a guess at all. It geometrically proves the exact value every single time.
So, here's our roadmap for today's explainer. First, the approximation problem. Second, geometry over magic constants. Then deriving exact pi, followed by exact phi. And finally, why exactness actually matters.
Section 1. The approximation problem. Let's get right into the inherent flaw in traditional computing that OMI was specifically designed to fix.
Well, in standard computing architecture, systems rely on what developers jokingly call magic constants. It's a sign-value model, meaning numbers are really just stored as a fixed surrogate sign, kind of like just slapping a label on a box without looking inside. The problem with that? It leads to inherent floating point errors. Because you're chopping off decimals just to fit data into memory, your state is only approximated. It's never proven. And honestly, when things are only approximated, you completely destroy the possibility of having perfect, verifiable determinism across a network.
Section 2. Geometry over magic constants. Here is exactly how OMI fixes this massive flaw.
Instead of relying on those cutoff approximations, OMI grounds its logic in finite incidence geometry. Specifically, it uses the phonoplane. You can think of this as a flawless geometric map. It consists of exactly 7 points and 7 lines, and every pair of points lies on exactly one line. It provides a perfectly exact, finite structure, and OMI actually uses this geometric space as its fundamental routing surface.
Which brings us to this quote, and it brilliantly illustrates the golden rule of OMI. In this protocol, mathematical constants are not stored variables sitting lazily in a memory bank. They are witnesses of an algebraic closure proven dynamically. Basically, you don't ask the computer, hey, what's the stored value of pi? Instead, you ask it to compute the structural geometry that undeniably proves pi.
In this exactness, it's incredibly powerful. By mapping the mathematical structure of that Fano-plane, OMI perfectly addresses exactly 5,040 slots in what it calls the Fano-addressed ring. What you should really take away from this is that it guarantees perfect addressability. We're talking absolutely zero data collisions.
Section 3. Deriving exact pi. Let's look at our first concrete example and see how this geometry builds a perfectly exact version of pi.
Okay, so here's how the derivation actually flows. First up, OMI maps that exact finite structure from the Fano plane. Then, it processes this through specific geometric pathways. These are known as chirality diagonals and Polybius phases. And from those geometric truths, it computes the Gregory-Leibniz expansion series. By tracking these exact incidences, OMI dynamically derives pi. It converges exactly to the true value, all without needing a single stored decimal point.
And the best part? This isn't just theoretical math drawn on a whiteboard. The OMI system explicitly proves this in a formal verification language called conc. The proof, which is known as OMI_pi_proof, mathematically guarantees that this geometric derivation is unequivocally equal to the true, undeniable mathematical pi.
Section 4. Deriving exact phi. Now, let's see how OMI applies this exact same geometric logic to phi, which you probably know as the golden ratio.
Just like with pi, there is absolutely no stored decimal for phi. Instead, the golden ratio emerges entirely naturally from the structural geometry of what OMI calls the rectified 35 common core. This geometry utilizes dual Schläfli symbols, which, by the way, are really just mathematical shorthands for describing properties of specific 3D shapes, and it uses those to map its 30 vertices perfectly.
The derivation steps here are remarkably consistent with what we just saw. The system grounds its geometry in that rectified 35 common core.
And because it's rooted in exact geometric incidence, resolving it naturally satisfies the classical fixed-point quadratic equation for phi, x squared equals x plus 1. This yields the exact classical phi, and once again, this absolute perfection is verified formally in Coq. Just look at this number, 0. That represents the exact amount of approximation error in the OMI theory when deriving these constants. No magic numbers, no floating point errors, 0 approximations.
Section 5. Why exactness matters. All right, we've gone pretty deep into the mathematical weeds today, I know, but let's step back and explain why this structural perfection is actually going to revolutionize the future of computing and networking.
These 4 pillars form the absolute bedrock of the OMI system. Exact, meaning literally 0 approximation error. Deterministic, meaning the exact same computation always yields the exact same result, no matter where you are in the world. Computable, meaning the math converges precisely for any required precision. And verified, meaning every single bit of this is machine checkable via those Coq proofs. These guarantees make OMI radically different from literally any computing technology we use today.
And because the math is flawlessly deterministic and exact, it unlocks something genuinely incredible. Multiple peers can perfectly synchronize open-world states just by sharing verifiable receipts with each other. There is no central database or global authority required to dictate the true state. The geometry itself proves it. It guarantees perfect deterministic replay, and it even ensures hardware execution safety through lazy evaluation. That basically means hardware only acts when a structurally perfect intent is fully 100% validated.
So, I'll leave you with this question. Are you ready for a computing future where systems don't just store data, but geometrically prove reality? It completely shatters how we currently think about data storage and computing. Honestly, when you strip away the guesses, the approximations, and those magic constants, you're left wondering what else becomes possible when our systems finally speak the exact, unbreakable language of geometry. Thanks for joining me on this explainer, and I hope it completely shifted your perspective on what computers are actually capable of.